Hi, everybody. Today is February 16th, 2026, and we are going to spend a little bit of time talking about a review of vector mathematics. The reason that we are talking about this today is because chapter 3 is going to start talking to us about rigid bodies, which means up to this point in chapters 1 and 2, we have talked about forces basically acting on points, which means if forces are acting on a point, whether it's truly a point or not, we sort of make an assumption. For example, you might have a payload being suspended by a hot air balloon, and you really look at the forces that are acting on this point. But the simplifying fact when you're talking about points rather than rigid bodies is that nothing is going to rotate, nothing is going to turn, nothing is going to be acted upon by a moment. You just have the summation of forces in all three vector directions equal to mass times acceleration, or if you are not accelerating, let's see, or summation forces equal mass times equals 0 if acceleration is equal to 0. Okay, so this was what we were talking about in chapters 1 and 2. In chapter 3, we start talking about rigid bodies, which is itself a simplifying assumption, because if you have a non-rigid or a deformable body, which we're going to discuss when we get into mechanics of materials, you can actually overstress or overload an object and deform it or break it, and you have to take that into consideration as well. But when we talk about rigid bodies, we're going to talk about bodies that have a size and shape, as well as a mass. But the assumption we make is they are able to bear whatever loads we put upon them. Okay. Oops, got to get that. All right. So we don't have to worry about it bending or breaking, but we do have to worry about it rotating. Okay. So in order to start considering this idea, we need to consider that this is where we're headed. We know, as always, if acceleration is equal to 0, summation forces have to equal 0 in all vector directions. But now we need to calculate moments. And what is a moment? Well, a moment has to be taken around a point, and it is, let's just do this. Any moment about 0.0 is equal to a distance vector multiplied by a force vector. So in order to do this vector math, we need to know how to multiply vectors. It also turns out that there are some intriguing properties of vector math. One, there are two types of multiplication. There is what is commonly called a dot product. And the dot product is itself a scalar. In other words, there is no particular direction. Now, when I say that, there are some directional properties of dot products, but they don't apply mathematically. What I mean by that is, if you, for example, have a vector that looks like this, let's call it vector V, and you have a vector that looks like this, which we call vector Q. Vector V dotted with vector Q is equal to the projection of V onto Q. okay? And so it's a magnitude, and one could argue it's in the direction of Q. That is correct. However, it's not enough of a directional property to make it fully vectorized. Similarly, you could have a projection of Q onto the vector V. And it turns out that both of these are scalar and they are also equivalent. In other words, a dot product in math speak is commutative, which means Q dotted with V is equal to V dotted with Q. All right. So if it's a scalar, how do we find a scalar from two vectors? Okay. Now I'm going to show you a little bit about the math, but I'm going to pick out two vectors before I get excited about that, just so that I can, actually, I'm going to find three vectors and we'll just do some math with those three vectors. I could make up my own vectors, but I often make up silly vectors that are like collinear or do something weird angularly. So I would just as soon find in your textbook a problem that illuminates three vectors, and we'll do a bunch of math with them. All right. Problem 35 gives us three vectors. Vector P, let me get a new piece of paper. In problem that I'm going to be working with P, the vector P is equal to 2i plus j plus 2k. The vector Q is 3i plus 4j minus 5k. And the vector S is negative 4i plus j minus 2k. All right. So if we talk about a dot product, let's say, what is P dotted with Q? Okay. To execute the algorithm that gives you the number, the magnitude of P dotted with Q, you take the X values, in other words, 2 and 3, you multiply them by each other. You take the Y values and add this product. J is just 1J times 4. And last but not least, we have plus the Z components or the Z quantities, which are 2 and negative 5. So if I execute this dot product, I get 6 plus 4 minus 10. 6 plus 4 is 10. 10 minus 10 is 0. So the other thing is that this is a commutative property. P dotted with Q is equal to Q dotted with P. So if I were to dot them the other way, and I said Q dotted with P, you can see why. That would be 3 times 2 plus 4 times 1 plus negative 5 times 10, or 2, excuse me, got carried away. So that's 6 plus 4 minus 10, which still equals 0. This is very important because a dot product is commutative, but a cross product, which we're going to do in a minute, is not commutative. They're not the same. So we'll talk a little bit about that in just a moment. All right. Now, the other thing that you can do that has limited use in our discussion is a dot product. If you take the magnitude of P and the magnitude of Q and multiply them by the cosine of the angle in between them, that is also equal to the magnitude of P dotted with Q. Okay. So sometimes this comes in handy, but the big deal here is the cosine of theta, the angle between those two vectors, determines what the dot product is going to be. So the magnitude of P here would be square root of 2 squared plus 1 squared plus 2 squared. And the magnitude of Q would be the square root of 3 squared plus 4 squared plus negative 5 squared, which is the same as 5 squared. But then in order for this to be 0, neither of these numbers, both of these numbers are non-zeros. So that means that the cosine of theta must be equal to 0. So if the cosine of theta is equal to 0, what is the angle between those two vectors? Cosine of what number?
90.
Yes. So that means that theta has to be equal to 90. So what does that tell me about these two vectors? It tells me that they're going to be perpendicular to each other. They're going to be 90 degrees. So in 3 space, it's hard to say if that's going to be immediately obvious, but P would be 2, 1, 2, 2, 1, 2. Okay. And Q would be 3, 4, negative 5. So something like that.
How did you know the angle was 90 without it equal 0?
Because the dot product had to equal 0. If the dot product equals 0, this is an alternative definition of those two, of a dot product. And so the angle between them has to be equal to 0 because the magnitude of P isn't equal to 0 and the magnitude of Q isn't equal to 0. So, all right, but let's do another set of vectors that hopefully is not perpendicular to each other, and we can see if we can find a whole bunch more stuff. So let's use P and S. So let's talk about P dotted with S. Okay, that's going to equal 2 times a negative 4 plus 1 times 1 plus 2 times negative 5. Let's see what we come out with here. This is going to be negative 8 plus 1 minus 10. So if I look at that, it's going to be negative 18 plus 1, which is negative 17. Okay, so that dot product is not equal to 0. That means we could expand so that also means that the angle between them is not equal to 0. Because if it was equal, or excuse me, it's not equal to 90. It's some other angle, right? So what is that other angle? Well, let's find out. What's the magnitude of P? It's the square root of 2 squared plus 1 squared plus 2 squared, which is the square root of 4 plus 1 plus 4, which is the square root of 9, which is a nice whole number 3. What's the magnitude of S? Going to be the square root of negative 4 squared plus 1 squared plus negative 2 squared, which is the square root of 16 plus 1 plus 4, which is the square root of 21, which is not a whole number, but it's not a terrible number either. So if I do the square root of 21, that value is 4.58 and some change.
When you multiply the two vectors.
Yes. You mean as a dot product?
Yeah.
Yes, okay, because like I said, there's 2 different kinds of vector multiplication. So right now we're just talking about the dot product. Excellent question. One of the meanings of a dot product is projection of one vector onto the other. Okay, so if you drew one vector and then the other vector, and you constructed a perpendicular line from the second vector up to the termination of the first vector, this distance right here represents V versus Q. If you went on from the other side and you did a perpendicular to the head of this vector to the termination of this vector, this would be Q dotted with V, or the projection of V onto Q. So this is the projection of Q onto V. This is the projection of V onto Q. And they are the same. But
when you do a cross, it would be different.
Yes. Yes. this, and when we do a cross product, is that what you're talking about?
Yeah.
Yeah, we'll do a cross product in just a minute.
Yeah.
We've almost had all the fun we can have with the dot product, so, which the real name for a dot product is a scalar product. Okay, but everybody calls them a dot product, and so do I, but I'm just telling you that in math language, if you talk to somebody with excellent, beautiful, impeccable math skills, who came up through theoretical mathematics instead of engineering, they would say scalar product. All right, just so you know. All right, but let's do one more thing. I've also told you that if I take the magnitude of a vector, of each vector, and I multiply it by the cosine of the angle between them, that is going to be equal to the dot product of those two vectors. So I have calculated the dot product here to be -17. And I know that the magnitude of P is 3 and the magnitude of S is 4.58. And that means that I can use this equation to solve for the cosine of theta. In other words, what is the angle between them? So the cosine of theta here is -17 over the product of 3 and 4.58, which I have, let's see. Okay, so if I take 17 negative, oops, wrong way, -17 and divide it by 3 and divide it again by 4.58, I get a value of -1.24. I have something wrong with that.
Cosine or radians versus degrees?
No, it's just my math somewhere along the line. Let me make sure here. And this is always a bugaboo. All right, so let's see. Make sure I want my vectors down correctly and consistently. Okay, if P2, let me write this down right here. P is, start right here, make sure I don't have this wrong. 2, I'm gonna write it in the other form, 2, 1, 2. And S is 3, 4, -5. All right, so the dot product of P and S is 2 times, yeah, see right off the bat. Oh, S is, yeah, see, I picked up the wrong vector here. -4, 1, and -2. Yeah, see, I picked up a bad number there, but that's just the way I do business all the time. So now 2 times -4, that's correct. 1 times 1, that is correct. 2 times -2. Okay. So 2 times -4 is -8. 1 times 1 is 1. 2 times -2 is -4. When I add those together, I get 8. No, excuse me. This is -12. So that's -11, isn't it? Okay. So then if I do the magnitude of P, 2, 1, 2, 4, 1, 4, 8, 9, 3. This is correct. But now S, -4, 1, -2, 16, 1, and 4, 16, 21, 4.5. Okay, so I hope I am correct so far. So this number is 3, and this number is 4.8, but this number is -11. Okay, there we go. So then if I take that, it's going to be -11 over that, which will give me a different number. 11 divided by 3 and divided again by 4.58 is 11 divided by 3 divided by 4.58 equals, cosine of theta is 0.8006. Okay, now I have a question to ask you. When I got this value for a cosine, -1.24, how did I know instantly that I have a bad number?
Has to be between 0 and 1.
That's exactly correct. Can only be between the absolute value of 1, -1 and 1 and 0. So yeah, so when I get a number bigger than 1, there is no cosine of any number that is bigger than 1. Because if you go back to a triangle, the cosine is,
How do you multiply numbers against the cosine?
nope, not here, not yet. I just solved for the cosine.
Oh,
And so when it comes out bigger than 1, I'm like, or smaller than -1, I'm like, well, I know that math didn't change. I know that was my fault. I know I have a math error there instantly. But because if you go back to the definition, a cosine of an angle is equal to the length of the adjacent leg over the hypotenuse. Is there any way that the adjacent leg can be bigger than the hypotenuse on a right triangle? That's correct. So I knew it was me, so I had to redo it, and I found my error. Okay, well, if the cosine of this angle is negative 0.8006, negative 0.8, oops, I gotta do it the other way. I want to take the inverse cosine of that number, negative 0.8006, and that gives me an angle of theta equals 143 degrees. So those two vectors are about like this to each other, but it's in 3 space. It's not necessarily the same plane, but wherever it is, I mean, they're gonna, well, I won't even get into that. But so there's gonna be an angle greater than 90 between those two vectors. So just from doing a dot product, I've learned a couple of things. I've learned the magnitude of each of those vectors. I've learned the magnitude of their dot product, and I've also learned the angle in between those two vectors. Okay. What questions do you have before we move on to a cross product?
Why would you want to use the dot product rather than a cross product?
They have 2 different applications. They have many, each of them has different sets of applications. So when we're talking about moments, you're always using cross products. But when you talk about projecting one vector onto the other, like this, you will always use a dot product. You'll also find out that there are many, many, many more applications for this than what we're talking about, but in terms of right now, that's what we're talking about. So, like if you were to say, here's a very simple example. What would you use a dot product for? Well, let's say that you're going to travel from Powell to Billings, Montana. Okay. And you know that you're going to go a certain distance to the east and a certain distance to the north. Okay. You can think of that as being the legs of a triangle, or you can think of it as saying, I'm going to go, say I draw a perpendicular from my east and go up. So I can say I go so many miles north and so many miles east. So that's one way to think about it. Or if you did it the other way, if you said Billings, Montana is, and I'm totally making these numbers up, guys, I have no idea. Billings might even be west of Powell, I don't know. But Billings is 10 miles east of Powell and 90 miles north of Powell. If you had a small airplane and you could fly in a straight line, you may want to know how many miles you would want to be able to fly, and that would be the hypotenuse of that triangle. So anytime you're talking about right triangle trig, you're talking about dot products. The other thing is sometimes you want to find the angle between 2 vectors, just like we did, and a dot product is a very easy way to do that. If you're just given these 2 vectors, and somebody says, what's the angle between those 2 vectors? You know, if it's in 2-dimensional space, I can see it pretty quickly. In 3-dimensional space, I have no idea. So if you do a dot product, you can pretty quickly and reliably find the angle between those 2 vectors. Okay, so those are some ideas. All right. Now, shall we do a cross product? A cross product, if your calculator will do this for you, please let your calculator do this for you. Jace, did you find a way, were you able to make your calculator do?
Program.
Excellent, very good, because you will do it very often. And as I told Jace came into my office and we were working on this, I said, I don't mean to attribute my own carelessness with arithmetic to you. I always make an arithmetic mistake when I do a cross product. I don't know why. I always have to do it twice. So if your calculator will do it for you, or if you can write a program to do it, that's awesome, because calculators, as long as you've done it correctly, will not have a problem. All right. So what a cross product is, a cross product, first of all, is perpendicular to the plane in which the vectors multiplied exist. And it follows, if you've had physics, the right-hand rule. Okay, so in 2 dimensions, this is what a cross product looks like. X and Y. You have a vector R, and you cross it with vector F. That means that if you use your right hand and you put your hand along the vector R and you curl it up into the vector F, you will get your thumb will stick out in the direction out of the page. Okay. What that means is that if R is purely I and J, and if F is purely I and J, that their cross product, R cross F, will be purely K. Okay, so 2 dimensions, the only dimension either into or out of the page is the Z direction, or the Z direction, which has the unit vector K associated with it.
Real quick, how did you find I'm trying to write down the notes.
Yeah.
The vector, the dot product,
Okay,
and the one where you had the 2 magnitudes multiplied by the cosine theta.
yes,
What did you do to find the cosine theta?
Oh,
Three
yep.
dimensions?
in 3 dimensions? Yeah, absolutely.
Sorry to hear about this.
Don't, it's okay. So if you look, that's why I keep all my notes till the end of the lecture. Okay, so I found the magnitude of P, found the magnitude of S. Then I used the equation magnitude of P times magnitude of S times the cosine of theta is equal to the dot product of P and S. So I have computed P and S, and I've computed the dot product of P and S. So -11 is the dot product of P and S. The magnitude of P is 3, the magnitude of S is 4.58. So it breaks down into this equation. I can solve for cosine.
This is not a solution to finding the cross product of everything. This is to find the cosine.
Yes.
Okay.
So when you're given 2 vectors, P and Q, you can find or P and S in this case, you can find a bunch of different stuff. You can find the length of each one of them. You can find their dot product, which is the length of the projection of one onto the other. And you can also find the angle in between them. So this is fully in 3 dimensions. It works in 2 dimensions as well.
It's magnitude of one times magnitude of the other.
Yes.
Cosine equals -11,
Exactly.
because -11 was your.
You got it.
scalar product.
Exactly. That is
Okay.
correct. Very, very good.
What angle would you get out of 3 dimension? What does that
Well,
represent?
It just, okay, that's another good question. So here it is.
That's gonna be both the x and y.
Yeah, it's the whole thing. So like, here's 2 vectors in 2 plane, right? Here's 2 vectors in 3 plane. It's whatever that angle is.
Okay.
Yep.
Okay.
Good questions, all good questions, you guys. All right. So now, going back to a cross product. In 2 dimensions, cross products can be pretty simple. Okay, one thing you can say in 2D, and I really hesitate, as you've probably noticed, I hesitate to teach too much things in 2 dimensions that don't extrapolate into 3 dimensions. And this is definitely one of them. So I'm just going to put it on my paper right away. One of the applications of a cross product is what's called a moment. And what a moment is a rotation. So the first thing about a moment is you always have to take it about a particular point. So in other words, if I take it about 0, right here, my 0, 0, my origin, I have r and I have f, right? So I can write the vector r and I can write the vector f. Well, it turns out that the magnitude of the cross product is equal to the magnitude, I'm just going to say the magnitude of the moment, because that's our major application at this point, is equal to magnitude of r times magnitude of f times the sine, and they call it phi, of the angle in between them. This has no applicability in 3 dimensions. Okay, so you can always do a cross product using solving a determinant. And so I would really like you to, in every single case, solve a determinant. So we have to show you what a determinant is, right? And we'll work from there. All right. If you use the program MATLAB, you can solve a determinant in a 1.5 seconds. It's awesome. MATLAB will do this for you. But the chances of you having MATLAB on your desk, well, if you were doing this all day, you would have MATLAB on your desk. Absolutely. But so I'm going to kind of, what's that? That's right, but not in a test. So I'm going to show you the old-fashioned way. Your calculator will also do this for you because it's pretty arithmetic intensive. The way that you solve for a cross product is you first construct a determinant. What a determinant is, it is a name for an array of numbers. And it's an array that has, I'm going to take those two, I'm going to take P and S, P crossed with S. It's an array of numbers that has a number of rows and a number of columns. And you can think about like a building with columns. Columns go up and down, columns are vertical, rows are horizontal. In this case, when you're doing a cross product between 2 vectors, the first row are the unit vectors I, j, and k. The second row are the components of vector p in the x, y, and z direction. And the final ones are the components of the vector s in the x, y, and j, or x, y, and z directions. And why is that? What was the answer I gave you? The unsatisfying answer I gave you in my office, Jace?
Why is what?
Why is this how the determinant works out? Because you don't know till you get into linear algebra. And then they will teach you how to do that and why you're doing it. So I'm just teaching you how to do it. Okay.
Yeah, I probably forgot because I was like, well, we can't invest emotionally in things.
That is good advice right there. Do not invest emotionally in this. When you are in linear algebra, you can invest emotionally and you will learn more, but we don't have time to teach it and we don't have a need to teach it in this class. All right, so I'm going to make my determinant based on the values that I have. IJK. And P is 2, 1, 2, and S is -4, 1, -2. So there is your determinant. So if you have, this is called a 3x3 determinant, and these will always come out to be a 3x3 determinant. You wish to break it into a series of 2x2 determinants. And the way you do that is you choose, this is first, second, you select a multiplier row or a column. And when we're at this stage of the game, It's almost always best to choose IJK as your multiplier rule. Later on, for different reasons, I'll show you that you may choose a different one and it'll just make the math easier. That's all. It's the same number, just if it's easier or not. So since this is a multiplier row, it means I'm going to multiply I by something, J by something, and K by something. Now, to complicate the situation, every element, row and column, this is element 1, 1, this is element 1, 2, this is element 2, 1, and so forth. Every element either has the same sign or the opposite sign, and they alternate. So element 1, 1 has the same sign, which is plus. J has the opposite sign, which is negative, and K has a positive sign. So if you went same, different, same, if you went down, it would be same, different, same. If you went across in the second row, it would be different, same, different. Okay, so if you choose the top row, it's always same, different, same, plus, minus, plus. What do we multiply by? Well, we create mini determinants that are formed by crossing out the row and column of this element outside of the multiplier element. So if I cross out the row and column that I exist in, I'm left with this for a determinant, 1, 2, 1 minus 2. And if I do the same for J, I cross this out and this out, I'm left with 2, 2, negative 4, negative 2. And then finally, if I cross out the row and column that K exists in, I'm left with 2, 1, negative 4, and 1. All right, now we won't do these, but you can have bigger element, you can have bigger determinants. Just a 3 by 3 is good in 3 space. A tensor, you may have heard of that, or a phasor, are actually higher order, solved by higher order determinants. But the good news is, if you have 4 by 4, you can break it down into 4 3 by 3s. And then you can break each one of those 3 by 3s into 2 by 2. And once you have a 2 by 2, you can solve this analytically using regular arithmetic. And the way you do it is, you take what's outside. I'm going to write this again just to remind myself where I am. You take the multiplier element plus I, and you look at this little determinant and you draw a crosshatch. And you take this times this, which is negative 2, minus this times this, which is negative 2, or minus a 2. Then you take a J, which is negative J, you multiply this times this, which is negative 4, minus a negative 8, which is a plus 8. And last but not least, you take K and multiply it by this times this, which is 2, minus 4, minus a minus 4, which is plus 4. So my answer is that P crossed with S is equal to negative 2 minus 2, which is negative 4 times I. And then I have negative J times a positive 4. So it's negative 4J plus 6K. And that is the answer.
What I got on my head.
That's a good thing, because I was gonna say the chances of me getting through this without making a arith mistake are very small. I said arith mistake. That is a great term for what I do, arithmetic mistake. So without making an arith mistake, this is the correct answer. Okay, now, oddly enough, if you have, like we talked about, dot products, scalar products are commutative. So Q dotted with V is equal to V dotted with Q. Cross products are not commutative. If we had here instead S crossed with P, the S terms would be here, the P terms would be here, and every one of my numbers here would have the opposite sign.
Is the magnitude of the cross product also the square root of those numbers? So the height of the moment, the force of the moment?
No, because it depends on the angle between the two vectors. It's an excellent question. In other words, the magnitude is the magnitude of each times the sine of the angle in between them. Mess with it, but it's fine. It's a great question, and I've never actually been posed that question before.
So we can find the magnitude of any vector except for a cross vector, a moment vector, by using its IJK components.
Hang on just a second. I want to write this down. I want to listen to that question more carefully. This one I want to say first of all is P crossed with Q is the negative, or P crossed with S is the negative of S crossed with P. Tell me your question again.
So P, we can find its magnitude by taking IJK squared.
Square, yes, yes.
We can't do that with the cross result.
Well, with this result here, you can. Yes, absolutely.
Oh,
P cross, you can't do it with the determinant, which is what I thought you were saying. So in other words, you couldn't say 2 squared plus 1 squared plus 2 squared plus 4 squared plus 1 squared plus 2 squared, and then take the square root of that. But yes, here, P and S, absolutely. Yes,
so P cross S, this number, which is -4 plus 6.
yes.
We can use that to find the magnitude.
The magnitude of P cross S is, as you're asking, 4 squared plus 4
Okay.
squared plus 6 squared square root. Yep, absolutely. And if you take this and get the magnitude of each of these, you can find the sine of the angle in between them, the two original vectors. Yes,
So when we multiply two vectors cross.
yes, cross product.
We're finding the perpendicular line.
Yes, we are.
To both of them.
Yes. Yes, so like if P and Q or P and S were in the same plane, like the XY plane, that's why the is purely Z, but if they're in some oblique plane, it's still perpendicular to whatever that oblique plane is.
Okay, so
Yes,
like this one
yes,
is going 4 on the X, 4 on the Y, 6 on the.
you got it. Yep. That's correct. Right, it is. There's a physical interpretation of one of the things about a cross product, or they're also just called vector products. Another physical interpretation is it's an axis of rotation. Okay, and it's a magnitude of rotation. So you can kind of think of it as a pivot point of those two vectors. If those two vectors were spinning each other, it would be the axis of rotation of the two.
So that's the moment.
It's the moment.
Why is it called a moment?
It's an old-fashioned term and a moment of a force. There's a lot of moments. There's moments of inertia. There's moments of moments. It's an old-fashioned term, just meaning it generally has to do with the rotation. It generally has to do with something rotating something else. How's that? It's kind of like they used to say, there's all kinds of words that have obsolete meanings. I'm trying, and now nothing's coming to my mind beside moment, but we only use it. So another, let's take a look here, Jace. Since we're on the subject. Why?
It's from Latin, momentum.
There you go.
Let's see if I find the rotation.
Oh. See, that's great. Comes from Latin and it means it's related to the idea of momentum. Okay, so there's another thing. So if you think about momentum, like linear momentum, which is mass times velocity, and mass is a scalar, and velocity is a vector. Momentum, linear momentum is a vector, right? It's also, you can think of it as being the extensive property. You can think of it as being extensive velocity. Like if you get hit with something that's going at 5 meters per second and it's quite small, it's going to hurt less than if you get hit with something large that's going at 5 meters per second. So it's an extensive property as well. So that's great. See, don't you love Google? She knows everything. All right, so that's it for today, guys. Work on chapter 3. I will be in my office. If you need me, come see me. And aside from that, have a wonderful week. And we'll see you next Monday, if not before.